All right, so we're going to start some actual Physics 200. This is Chapter 21, Electric Charge and Electric Fields, okay? So here is sort of an outline of where we're going to go. We're going to start by talking about what electric charge is, where it comes from, and then we'll talk about different materials and how they interact with electrical charge, okay? Then we'll introduce some math at Coulomb's law, and then we'll start introducing some more like hardcore physics, like what is the electric field, how does that create a force, okay? Then we talk about how to calculate electric fields, how to visualize electric fields, and then the ever interesting electric dipole, okay? All right, so let's just start by what we already know. How many of you have shuffled across a carpet and then touched your friend or family, making them jump? Okay. Many of you have never tried that, have never shocked anyone. All right. Yeah, go those plastic slides you had to be on as a kid because the metal ones were unsafe already. Those definitely create some static electricity, and you can shock people, or you could get shocked. If it's just a dry day and you touch your car sometimes. However, just a note, if you touch like a table or a doorknob inside and it always shocks you, you might want to talk to an electrician, okay? If it only shocks you like on dry days, it wouldn't like, you know, and you feel like long hair and you're like generating a lot of static electricity, that's fine. But if there's something that you touch and every time you touch it, it shocks you, that's probably a grounding issue. So you should speak to someone about the circuitry of the building. So dragging your feet on the carpet, touching metal on a dry day. And why is it a dry day?
Because I'm sure air doesn't.
Yeah. What about humidity?
Water.
Yes, water is a conductor. Also, you are a conductor, and a lot of metals are conductors, okay? So that's anything that electrical charge can easily move through. And we'll talk about the structure of conductors and why that happens in a little bit, okay? So dry days, those are days that you're going to have much better electrical charge storage on an object. If it's humid, then that little bit of charge starts to diffuse out into the air, and then you lose your charge. Because most things are electrically neutral, right? So touch the table. Did it shock you? I hope not, because it's not even a conductor. So you're electrically neutral, right? You're not always going around shocking people. Sometimes you end up with a little bit of extra charge, but it's pretty easy to discharge it. That's why once you get some, it's pretty easy to shock people, okay? If you want to scale up a little bit, lightning is just a really big electrical shock, okay? So here, if you have charge build up in clouds because of different pressure and some friction sort of in the air up in the atmosphere, you build up some charge. Once you have a charge difference up here from the ground, okay, you end up with something that looks like this. And that's like slow-mo with a high-def camera. So what's really interesting about lightning is that we don't know that much about it aside from like the big thing, which is it's like electrically, it's like a dielectric breakdown from clouds to earth, which is kind of insane. We'll talk about dielectric breakdowns when we talk about capacitors. Yes?
Clouds are made out of condensed water. Why does an electric charge diffuse the cloud?
That's a good question. Maybe you should be a meteorologist. I don't know the answer to that question. For the main thing is like it does, right? It can diffuse through the cloud, but the difference is it stays in the cloud rather than diffusing out into the air, and then it has to release all of that charge into the ground. So that's the broad definition of what's happening. But what's crazy is you see like this goes all the way down, and then you have the big lightning that you see coming up. Like you don't actually usually see this. This is slowed down like over 100 times so you can see what's happening. But anyway, fun with high frame rate cameras. Okay. So let's talk a little bit about electric charge and what it is. So everybody knows the dumb model of the atom, right? So what is an atom made up of? Protons, neutrons, electrons. What's the structure? Protons and neutrons are in the middle. And honestly, if this is like the nucleus and you put it in the middle of the room, the electron would be like the whole rest of the room and then some. Okay, so the electrons are way out there, flying around-ish in a like quantum way. It's like a fuzzy statistical cloud where you can't tell where they are, but they're everywhere and they're somewhere and they're going fast or not. So if you want to learn about that, you can take 210 and we'll talk about that in a little bit more depth. But basically, in the middle, you have this nucleus. What charge does that nucleus have? Positive, because it's made mostly of protons and neutrons. And what charge do neutrons have? Yeah. Was it a neutron walks into a bar and asks the bartender, how much do I owe you? It's like, for you, no charge. See, we've got 2 jokes already. And so, yeah, the nucleus is positively charged. The electrons are negatively charged. Okay, anybody know the scale of an atom in meters? 10 to the what? That's a little small. 10 to the negative 24. That's so tiny. Negative 10. Right. The width of an atom, sort of the radius of an atom, is on the scale of 10 to the negative 10. Now remember, 10 to the negative 9 is called what? Nanometers. Okay, and in hundreds of nanometers, that's the wavelength of light. Okay, so this is why light and atomic transitions go pretty closely together. They're the same scale. All right, but a hydrogen atom is about 10 to the negative 10 across. All right, so here's a model of a very small atom. It's about 10 to the negative 10 across. This is our very dumb version of the atom, but all of these things have charge, and we left the neutrons out because who cares? Okay, we're not talking about mass. So electrical charge has the variable Q. All right, sometimes we use small q, sometimes we use big Q, but the variable Q is for charge, which makes so much sense because there's no Q in the word charge. But whatever, I'm sure there's some reason. And we measure it in coulombs because we like to name all of our units after old dudes. Okay, so coulombs with a capital C. All right, anybody know how many coulombs are in one electron? Doesn't matter, you don't have to know that. Fundamental unit of charge, E is 1.6 times 10 to the negative 19. Now, I'm not going to ask you to memorize this, but you might want to at least get a sense for the scale. 10 to the negative 19th is pretty darn small, okay? And this will come up, so you don't have to memorize it, but if you have a cheat sheet, you might want to include that because often you will be asked about electrons or protons. They have the same charge, okay? A proton also has 1.6 times 10 to the negative 19 coulombs. What's the difference between those charges, though? Positive and negative. An electron is 1.6 times 10 to the negative 19 coulombs negative. A proton is positive 1.6 times 10 to the negative 19 coulombs, okay? And so anytime you see E, it stands for this. And it doesn't include the negative. So if you see E, that's the charge of a proton. If you see negative E, that's the charge of an electron, all right? So yeah, here's that written out, all right? So let's think about where charge comes from. So if you have a charge, if there's a charge on you, what does that mean?
Electrons around?
Yeah, you have extra electrons or you've lost protons, okay? So all charge comes from protons and electrons, all right? Because what happens if you cut an electron in half? Can you cut an electron in half? No, right? That is a particle that cannot be broken down further. So the smallest unit of charge, and yes, you can break a proton into quarks, but it's not that easy. So for the most part, unless you're in some sort of weird quantum state where like you're in a high energy situation or there's high temperature or high pressure, which in most everyday life there isn't, okay? Protons and electrons are the smallest possible unit of charge. Even though you can break a proton into quarks, it doesn't happen under normal circumstances. Okay? And it doesn't stay that way for a very long time. So protons and electrons are the smallest possible unit of charge. So that means they are the fundamental unit of charge. And that means we can introduce a new term in physics, which is that charge is quantized. Does anybody know what the word quantized means?
Fixed at a certain level, but it can't be less than, more than, something like that?
Kind of, yeah. So quantized is really a fancy word that means it can be broken. If you divide it up, it has to give you an integral result. Okay, what does integral mean? No, well, no, what about, I mean, in terms of numbers? Integer result.
Oh,
Whole numbers, okay? That means it can only be broken down into whole numbers, all right? So if you know how many electrons are in something, it has to be a whole number of electrons. Okay, so you have a certain number of coulombs of charge, and you divide it by the charge of an electron, it should give you a number like 7 or 10 or 5 or 2 or 900, but it can never give you a number like 1.372, okay? Because if there's charge in something, it's made up of electrons, and it has to be a whole number of electrons, all right? Now this sounds like it's not that big of a deal, but remember, whenever we do anything like integrating and differentiating, we're assuming that physics is continuous, okay? That's the continuous approximation, because otherwise it's a sum. If you have to count individual things, you have to use a summation. And I don't know how far you are in math, but it works out a little bit differently. Some things sum and integrate the same, but some things don't. There's some difference between summations and integrations that comes from the granularity of what you're using, okay? So usually when things are really, really small, it's almost the same. Continuous and all that, it's all the same thing. But you can reach a limit where it's not, okay? And that's what we do in quantum mechanics. We realize if things, that's why it's called quantum mechanics, right? Things that don't break down further than a certain small amount. So that means you have to sum them up. And that means as you get close to that limit, you have to use slightly different math to understand what's happening, because you can't have half an electron, a third of an electron, a quarter of an electron. Okay, you can only have one whole electron. So when you get really small, things get a little bit weird. All right, and that's just a preview. For our purposes, though, this is the first thing we're really introducing that's quantized. Okay, and it makes physical sense, right? It's like if you have a bunch of marbles and you want to know how many marbles are in a jar. Okay, you're not going to estimate that it's 500 and a half a marble, unless you could see there's like a broken marble in it, okay? Let's say they're unbreakable marbles. This is a bad analogy. All right, so moving on. So basically everything's made up of atoms, and atoms have both positive and negative charge. So what does it mean when we say something is neutral, electrically neutral? Does it mean it's made up of neutrons?
Charges are balanced.
The charges are balanced, right? Because you know your electrical charge currently is neutral, okay? That means that you have the same number of positive and negative charge, right? And most atoms have the same number of protons and electrons in their like most stable state, okay? So that's not surprising, but it just means electrically neutral doesn't mean you don't have positive and negative charges. It just means you have the same number and they're fairly evenly distributed. Okay, and that's an important distinction because it explains things when you start bringing charge into things and charges start rearranging. You can get things that are electrically neutral to behave as though they have a charge because you can shift the charges around and do something called polarize them, where one side has more positive charge, the other side has more negative charge, but they still have the same amount of charge, okay? The other thing is charges can't be created or destroyed. We can't spontaneously have electrons appearing and disappearing, all right? And even if you have something crazy like a electron-positron annihilation, you lose both a positive and a negative, so that cancels out nicely. Anybody ever had a PET scan? PET scan. So, like, we won't go into that yet. We're getting a little carried away. All right, so positive ions just mean you have more protons than you have electrons, okay? What do you think negative ions means? Yeah, the opposite, right? So you'll have more electrons than you have protons, okay? So an object is positively charged if it has less negative charges than it has positive charges. And it's negatively charged if it has more negative charges than it has positive charges. Yes?
So we call those ions
I mean, you can call them cations and anions. I just, I'm not teaching chemistry, and we don't actually need that terminology for this class, so I try to keep it simple. I'm just showing off your chemistry skills. All right. So basically in math, what this says is the total number of positive charges minus the total number of protons minus the total number of electrons times the charge of one proton or electron. Okay? And you can see here, if you have more electrons, is this going to give you a positive or negative answer? Negative. If this number is bigger than this number, your whole answer is negative. And so you multiply a negative number by E, and it means you have a net electron charge. Okay? What? E is constant. It's 1.6 times 10 to the negative 19 coulombs. Okay? So the charge of any object is the number of protons minus the number of electrons times this fundamental unit of charge, the charge of one proton or electron. Okay? And of course, charge is quantized. It means, so in math, that means it's made up of integer values of that, or it's discrete, right? So it's a little bit special. All right, let's try a clicker question. So the way clicker questions work in this class normally, if it's one of these questions, is you take about a minute, you answer it without discussing it with anyone else. Okay, so you sort of just figure out where your knowledge base is. Then we look at how the class has responded, and we take another minute and you guys discuss it amongst each other and try to convert people to your personal belief system about this question.
I don't like that you phrase it like that.
So, it's like, okay. All right, let's discuss this and vote again. Much better. All right. The answer is going to be D. Why? Yeah, you cannot have half an electron. So you can't have 4.5. Well, I guess in this case it would be protons because it's positive. But you can't have 4.5 protons. Okay? You can only have whole numbers of protons. So how many protons do you have in part A? 1. How about in part B? What do you have in part B? Yes, 17 electrons, right? So 17 actual electrons. What about C? 1 mole of what? 1 mole of electrons. It's a whole number. It's a giant whole number, but it's a whole number. Okay? D can't have half a proton, and this would be 122 protons. All right? All right, let's think about that a little bit differently. All right? So let's discuss this one. It'll take about a minute and a half. Really get in there. Better. So let's go through this. So remember, when you divide Q by E, you should get a whole number. Okay, and remember E is 1.6 times 10 to the negative 19 coulombs. Okay, that is the smallest charge you can get. So this first one, is that bigger or smaller than 1.6 times 10 to the negative 19? Smaller. That means you have less than 1 charge, less than 1 E. Is that possible? No. Okay. If you divide this by 1.6 times 10 to the negative 19, what do you get? 20. Okay, well, negative 20. So that means you have negative 20 electrons. Okay. If you divide this, it's big, so you'll get a whole number. This is also big compared to that, so you'll get a whole number. So all of these will give you whole numbers when you divide by the charge of 1 electron or 1 proton. And so, but this one doesn't. Okay, this one is smaller than an electron or smaller than a proton. Okay? All right. Here's another one. Okay, we're mostly thinking B. Let's discuss. We'll vote again.
Okay.
All right. Although we lost 4 people, but hopefully you're still alive out there. We should go looking for people. So this is plus E, right? Minus E, minus 2E, and 0. So this is most negative, second most negative, neutral, positive. Okay, so that's going to be B, which most of you know. maybe that didn't actually change, just the other people disappeared. Okay, so let's actually do some math. Very easy math. Let's say we have a glass rod and a piece of silk. They start out electrically neutral. After we rub them together, 1,000 electrons jump from the glass to the silk, and we want to know the final charge of both materials. What do we think? What's the charge of the silk?
Negative 1,000 E.
Yeah, negative 1,000 E. Okay, what's the charge of the glass? Positive 1,000 E. Okay, so there we go. Should look something like this. All right, so let's talk about electric charge and actually some nomenclature. So the ancient Greeks noticed that you could generate electricity by rubbing amber with fur, like this. It wasn't exactly like this, but something like this. So guess what electron means? Cat. That's actually a good guess. What's the other thing it could be in this situation? Amber, right? Yeah. So electron means amber because, well, they didn't know what electrons were. They just you think about this. The ancient Greeks, they didn't have a model of the atom. They didn't have plugs to plug things in. They were just rubbing cats on rocks, and they were like, now it shocked me. Okay, so no, they weren't actually using cats.
How much they rubbing rocks on cats?
I don't even know if there were cats involved. I just thought this was a much funnier way of presenting it. It was probably something more like this, which is I think it used to be a bunny. No, it didn't. I think this piece of fur is actually older than I am, but just so if it makes you feel better, this bunny died a long time ago. Anyway, electron means amber, but what happens on the molecular level? Well, here's a molecule, okay, and this is a neutral molecule. It doesn't have a particular charge, or it has the same number of positive and negative charges. And remember, we know electric charge is conserved, okay? So we are not going to magically gain or lose electrons or protons in the process, okay? So here's the atoms. Here's some atomic bonds, all right? That's how molecules work, in case you were wondering. And let's add some friction, okay? So some sort of friction. This thing gets torn in half-ish. Okay, so now it has these two pieces. This would be the positive ion. This would be the negative ion. Now, if you add this all back together, right, you still have the same number of positive and negative charges. The whole thing is electrically neutral. But now that you've broken it apart, this one's a little more positive, and this one's a little bit more negative. Okay, so that's how we usually generate static electricity. So that's why when you shuffle your feet across the carpet, what's happening? Yeah, you're building up charge. You're either ripping electrons off the carpet, or the carpet's ripping electrons off your socks or feet. Okay, so it sounds really brutal, but it's super tiny and it doesn't matter that much. So just go like this. That's some friction. And of course, positive and negative charges attract. Okay, this is a lot like what basically our main experience with this is magnets, right? If you have north and south, they attract. If you have north and north, they repel. If you have south and south, they repel. So opposites attract, likes repel, okay? At least somebody got it.